All right, let's just jump right in. We're going to talk about logic today, but probably not the kind you're used to. We're going to step beyond that simple black and white world of true or false. Because it turns out, the word not, well, it can get way more interesting than you'd think.
So, let me ask you this. Is everything really just true or false? I mean, think about it. Our entire digital world is built on this binary, right? On or off, 1 or 0. But is that how reality actually works? Is that the whole story? What if not means more than just, well, the opposite of is?
You know, on the one hand, you've got the classic not we learned in school. It's just a simple switch, right? The light is on versus the light is not on. Super straightforward. But on the other hand, logicians and philosophers, they're playing in a much bigger sandbox. For them, not can mean things like, I reject that idea, or I deny that's true, or even something subtle like, there's just no proof for that yet. These are all totally different flavors of not, and each one needs its own way of being handled.
Okay, so let's really dig in and go beyond this simple true or false idea.
And here's the wild part. You would think the word not would be super easy to define, right? I mean, it's one of the most basic building blocks of logic. But it's actually surprisingly tricky. This research we're looking at highlights that it's maybe the most important concept in logic, but trying to nail down its meaning, it's a massive challenge. This isn't just a fun little riddle, it's a really deep philosophical problem.
So, what do you do with a problem like that? Well, that's exactly where this research comes in. Logicians aren't just sitting around talking about it, they're actually rolling up their sleeves and building brand new logical systems from the ground up, designed specifically to get a handle on all these complex, sophisticated shades of not.
So what exactly are these new types of negation? Let's check out a couple of the big ones.
First, you've got what's called empirical negation. Now, forget about abstract, pie-in-the-sky logic. This one is all about the real world. It's tied to observation and evidence. So when you say something is not true here, you might mean we literally have no evidence for that, or the data just doesn't back that up. It's a not that's grounded in what we can actually see and measure.
Okay, and then there's co-negation. This one's a little more out there, a bit more abstract, so stick with me. You know how implication is the classic if A, then B? It's about what has to follow? Well, co-negation is kind of its mirror image. It's about what's impossible. It's a way of formally saying, nope, that can't happen. It's not just denying something, it's about closing a door and ruling out a possibility entirely. It's a really cool specialized tool for logicians.
So, right, we have these awesome nuanced ways of saying not. But that brings up a huge question. How do you actually use them in a proof? How can you build a system around them that you can actually trust? You can't just eyeball it. You need a very special kind of tool built for this exact purpose.
And that brings us to the really cool part, the new tool that makes all of this possible.
This tool is called a labeled sequent calculus, or LSC for short. Look, the best way to think about it is like a super detailed blueprint for a logical argument. And the secret sauce is right in the name, the labels. These labels are like little sticky notes you put on every part of your proof. They track context, things like, this is true in scenario A, or this depends on this piece of evidence. By building that context right into the proof, LSCs can handle all those tricky negations we were just talking about.
So what does this look like in practice? Well, imagine you're building a legal case. First, you state your main argument. That's your proposition. Then, for every piece of your argument, you add one of those labels, right? You're tracking where everything fits. Next, you use a set of really strict, airtight rules to connect all the dots. And by the end, what you have isn't just, I'm right. You have a completely transparent, step-by-step, verifiable trail showing exactly how you got from your starting point to your conclusion.
But here's the thing. Just having a blueprint isn't enough. For these logical systems to be truly bulletproof, they have to meet what is basically the gold standard in the field.
This quote from the research really says it all. The holy grail here is something called cut elimination. Honestly, this is a massive deal in proof theory. The goal is to make your system cut-free. So, what on earth does cut-free actually mean?
Okay, think of it like this. A proof that has a cut is like using a shady back alley shortcut. Yeah, you might get to your destination, but you have no idea how you got there. It involves these weird, unexplained jumps in logic. But a cut-free proof, that's the scenic route with a perfect map. Every single turn is planned. Every step follows logically from the last. It's clean, it's direct, and you can trust it 100%.
And this is why being cut-free is the absolute goal. It gives you an ironclad guarantee.
It means your final conclusion comes only from what you started with, and nothing else. There are no hidden assumptions, no magic tricks, no leaps of faith. It is the very definition of a rock-solid, trustworthy proof.
All right, so we've been deep in the weeds of some pretty abstract stuff. The big question is, why does any of this matter? What's the so what for the rest of us, outside of a university logic department?
Well, it matters a whole lot, actually. At its core, this is all about building systems we can trust. When we have these transparent, reliable proof systems, it expands our understanding of really basic human concepts like denial and rejection. But it goes way beyond that. Think about computer science. We're talking about proving that life or death software, the code running a plane's autopilot or a medical device, is absolutely positively bug-free. This is the kind of foundational, rigorous logic that makes that kind of certainty possible.
And that kind of leaves us with a really mind-bending question to chew on. This whole journey shows us that even an idea as simple as not can be completely reimagined. So if we can give not a massive upgrade, what else is on the table? What other basic building blocks of how we think and reason are just sitting there, waiting for their own breakthrough? It's a pretty exciting thought. Thanks for diving in with me.